So I'll spend most of the talk kind of on the introduction, going over a bit of the preliminary, some of the definitions that I think will be helpful, motivating the study, going over the research scope, and then really getting into the background and the key idea behind this research. It's a simple single idea that we shows some promise for improving the operations of shared ride services. I'll cover the research methodology, the case study, which is in Anaheim, California, go over some results briefly, and then we'll spend some time talking about the conclusions of this study and really where we think there's potential to do even better in terms of operating these services. I'll be focusing today on mobility on demand services with shared rides. So mobility on demand, you might think of as Uber, Lyft, Via, microtransit, etc. The first one is without shared rides. That's like the UberX conventional Lyft services, your conventional taxis as well. But I'll be talking about the shared ride mobility on demand services. So these are things like Uber Pool, Lyft Line, multiple sets of travelers, likely strangers, sharing the vehicle at the same time. There's a service Via. There used to be two other services called Chariot and Bridge. They no longer exist. And they're also similar to quasi-paratransit services operated by public transit agencies, as well as new microtransit services that agencies like LA Metro are now putting out there on the streets. An important distinction that I might even mess up along the way is between paths and routes. So they're generally synonymous, but I'm going to try to make a distinction here. For me, a network path is the set of links and nodes, or you can think of them as street segments and intersections that a vehicle traverses as it moves through a network. So think of that as what Google Maps gives you, exactly where to make your turns, left and right, what intersections that's going to occur at. Whereas a vehicle route or a route is a sequence of pickups and drop-offs, really an ordered sequence of pickups and drop-offs. So that is, I'm going to get picked up first, Dr. Juliana is going to get picked up second, she's going to get dropped off, and then I'm going to get dropped off after that. So that's the route or the sequence. Okay, so motivation, there's a lot of potentially great benefits associated with shared ride mobility on demand services. I'll come at this from the individual level, that's you and I as travelers, from an operator perspective, as well as from a societal perspective. So from an individual perspective, it's another mobility service that's out there on the streets. You have the ability to maybe have a cheaper option than conventional Lyft or taxi because you're essentially splitting the fare amongst multiple travelers that are moving in a similar direction. Because the operators you see on the next slide is going to have a smaller fleet and lower operational cost, those costs can be passed on to you as the individual. From a mobility service provider's perspective, because you're using your capacity or your vehicles more efficiently, you can reduce your fleet size. And because it requires fewer miles if you're sharing or travelers are sharing trips, you can also reduce your operational costs, mainly your fuel costs, or your labor costs if we're in the case of human drivers rather than automated vehicles. I'll kind of switch back and forth between automated vehicles and current Uber and Lyft type services, but I will effectively assume that the drivers in the Uber and Lyft fleet comply with any direction that their Google Maps or Uber app tells them. So from a societal perspective, a reduction in vehicle miles traveled, which means a further reduction in congestion, fuel consumption, energy emissions, all the benefits of taking vehicles off the road. Yet, despite all those benefits, as I mentioned or hit on a couple slides earlier, Bridge, which is a microtransit or shared ride mobility on demand company, and Ford's Chariot service have both went out of business. Both of these went out of business before the pandemic, so we can't blame the pandemic on this one. They just weren't really making any money. They were not financially viable. So you might say, but what about Uber Pool and Lyft Line, right? These are existing shared ride mobility on demand services. Depending on where you're getting your data from, at most 40% of trips in Uber and Lyft are shared at all, but I think a better estimate is probably closer to only 20%. That is, most people were just getting the conventional UberX service or base Lyft service where you're not having to share with any strangers in the vehicles. So what are some of the challenges? Why is this occurring? And how can we address this with research and through practice? I think the first and most likely one, which I won't be getting into today, but I have done some other research understanding some of these behavioral underpinnings, is that people, humans, have an aversion to sharing things, in particular sharing space in vehicles. And of course, this is likely only increased because of the pandemic. The second, which is what I'll be talking about today, is that operating these vehicle fleets is quite challenging from many perspectives. So there's really trade-offs between how much you should detour to pick up the other person that wants to ride in the vehicle. If you detour farther, that means it's an inconvenience to the passengers that are in the vehicle. But if you're willing to detour farther, that means you can have more sharing opportunities as well as reduce the costs on average for the travelers. There's also uncertainties or stochasticity everywhere in the system. From the operator's perspective, the main area of stochasticity is the requests themselves. Because most of these are on demand or real time or immediate, people make a request and want to be picked up immediately. The operator doesn't know exactly where those requests are going to pop up before the requests are actually made. So there's also uncertainty associated with the travel times of the network. You might think of this as congestion, right? You don't know exactly where congestion is going to arise. You don't know the impacts of that congestion. And even the pickup times and the drop-off times, more so the pickups, there's uncertainty there. That is, the vehicle arrives at the person's requested pickup location, but they're still upstairs, in the shower, in the extreme case, or they're just around the block because they can't find the vehicle or they can't find exactly where their mobile app told them to be. So all of these things impact the efficiency of the operations. I have done so today we'll be talking about these trade-offs implicitly. I have done some previous work about the pickup uncertainties, and inherent in all of the research on operating shared ride services is this uncertainty associated with the new requests. I won't be getting into it today, but another important question is what are the potential policy interventions associated with shared ride services? Right? Do we want to encourage them heavily, either through sticks or carrots? That is, right now, a number of cities have tried to force Uber and Lyft or push Uber and Lyft in the direction of having more shared rides as opposed to their services where it's just one passenger request in a vehicle at a time. Okay, so that's a bit of an introduction. Let's get into actually what this study was about. So I'm going to first conceptualize the idea of bi-criteria pathfinding. Bi-criteria means two different criteria for these shared ride mobility on-demand vehicles. I'm going to develop a modeling framework both for the static operational problem, which doesn't make much sense in the context of mobility on demand, but you'll see that it might be useful, as well as the dynamic case. That is the realistic case in which these vehicles are operating in the real world in real time and requests are popping up throughout the day. I'm going to propose a solution algorithm, or really what it is a policy or a strategy for how the fleet provider should respond to these requests as they come in and how they should route the vehicles or assign the vehicles to pass through the network. And then I'll do some testing of the algorithms and models as well as some validation of those using the case study of Anaheim, California. We also did some testing in Sioux Falls, South Dakota. For those of you in transportation, or I guess maybe particularly network modeling, the Sioux Falls network is a common base case, but it's not very realistic, so you have to move to more realistic networks to get some interesting results. Okay, so I talked about how there's a number of operational sub-problems associated with operating a shared ride mobility on-demand service. So the three that have been largely recognized explicitly in practice by Uber and Lyft as well as in the research is matching passengers to vehicles. That is, which vehicle do you get assigned to once you make a request? There's also the routing or sequencing. This is very simple if you only have one or two requests inside the vehicle at one time. Once you start allowing more requests inside the vehicles, the size of this problem becomes quite large in terms of the number of possible combinations of options for the requests or for the sequencing. The third is repositioning empty vehicles. So if you have an asset that's not being used right now that is a vehicle, where should you place that vehicle? Should you leave it where it is and hope a request pops up around there? Or should you move it to another portion of your region where you expect demand to arise in the near future? And the fourth, which I'll be focusing on today, is pathfinding. So the strategy that's been implicit in, as far as I know, every single shared ride mobility on-demand service in the literature and in practice is just to call your Google Maps algorithm, which gives you the shortest path from your current location to the next place you want to go. I mean, that makes sense, right? Why would you not want to just move to your next location as quick as possible? So what this research hypothesizes is that it lacks foresight. It's a little bit myopic to do just that. Because you're assigning vehicles to the shortest path between your current location and the next pickup or drop-off location, you might be missing out on paths that are going to move your vehicle that has extra capacity inside of it through parts of the network that are going to have demands that are moving in the same direction as the vehicle. So I'm not that familiar with Los Angeles, but in my mind, I always come back to the Chicago example. So Chicago has a highway or a freeway that runs along the lake that goes north and south, and it's about 3 miles east of the main corridor where a lot of things happen on Friday and Saturday nights. And that corridor is where all the demand arises. So in my mind, you'd want to move the vehicles, if not along that corridor itself, because it might be congested, at least somewhere near that corridor. But what Uber and Lyft always do is pick up a traveler in that main corridor, drive 3 miles east to the river, to the freeway there, head north on that freeway until the person needs to get off at their exit, and you never find another match once you're on the freeway. So you'll see that graphically here. So I have two different paths between, I have here the user one's pickup location, but you can think of the triangle as the vehicle's current location, as well as the star, which is user one's drop-off location, or your next pickup or drop-off location. I have two different paths. I have the purple path, which is the by criteria path, and the red path, which is the shortest path. So these numbers are the linked travel times. You can see they're slower at the top and much faster at the bottom. And then the shading of the green, the darker it is, the more the demand there is in that area. So the idea is, instead of leaving the high demand area, getting yourself to the freeway as quick as possible, and then finally getting off at the exit here on the highway and going to the person's destination, you would find a trade-off solution which moves you through not the slowest, highest density corridor, but rather a corridor that's reasonably fast, has reasonable demand or moderate demand at its level, but is also near the high demand area. Okay, and this is just a broader example to really drive it home. If you're going from Chicago to Pittsburgh, the shortest path you can see is along I-90 in the north there, but if you know there's going to be another pickup for your truck around Fort Wayne, Indiana, you might route your vehicle through Fort Wayne, Indiana, in hopes that that new request pops up before your truck gets there. There has been some research in the past in the truck routing literature, which is what I'm trying to emphasize here, that has similar ideas about not always assigning trucks to the shortest path, but rather moving them through or near cities where a new demand might pop up as they're traveling across the country. So the goals here, develop an efficient operational policy for these services that does the matching problem, solves the routing or sequencing problem, repositions the empty vehicles, and assigns vehicles to path through the network, considering the two criteria: travel time, which is associated with the shortest path, and a new criteria, which is potential future demand. We're going to try to answer the following questions once we have these 4 operational sub-strategies in place. Does this by-criterion pathfinding improve operational efficiency? If yes, when or under what conditions should these vehicles be assigned to the by-criteria path as opposed to just the shortest path? And then what are the major external factors or internal or endogenous factors that impact the effectiveness of the by-criterion pathfinding? So this is basically the same set of steps shown in graphical form here. So at each time instance, you can think about this as every 2 seconds, or every 5 seconds, or every 15 seconds, the fleet controller, fleet operator is going to look out there, look at all the new requests that haven't been assigned a vehicle yet, as well as the status of all the available vehicles in the network. It's going to first determine potential feasible matches between the travelers and vehicles. It's then going to calculate a cost for each of those potential vehicle traveler request combinations. Trying to minimize the sum of those costs, it's going to match the vehicles to the travelers. After the matching process, if there are empty vehicles, the empty vehicles are possibly going to be repositioned throughout the network to better serve future demand. And then finally, after the matches are made, the vehicles are going to be assigned to paths in the network, sequences of links and nodes, based on this by-criterion approach. So a little bit more details on the cost measure. So for a vehicle that already has a request inside of it, we're going to look at its existing route, or I guess, route's fine. We're going to look at its existing route, which is displayed in green here. And then we're going to see the new route, which involves a new pickup for passenger 2. And we're going to calculate the difference between those. Our cost metric is going to be purely distance, but it could also include travel time as well. So the matching problem is quite common in the operations research literature and in practice. Uber and Lyft are solving this problem all the time. There are different ways to solve it, but it's simply trying to match a set of passengers to a set of vehicles. I won't get into the details too much, but this is the bipartite matching problem or the assignment problem. It has a really nice property. That is that it has the total unimodularity property, which means that even though you need to assign a single vehicle to a single request, that is, you have binary decision variables, if you relax that constraint that a single vehicle must be matched to a single request in your formulation, it doesn't matter. It'll still always return integer solution. It'll always assign one vehicle to one request. You won't ever have a half a vehicle assigned to a request or a quarter of a vehicle assigned to a request. So this allows you to solve really large problems. Tens of thousands of vehicles, tens of thousands of requests every few seconds, and it doesn't take too long to solve the problem. So the two parameters of interest, aside from the decision variable is x, matching passengers to vehicles. The reward p is how much reward. You can think of this as the added revenue or the associated profit associated with each request is rp. And then the cost, which is really the travel time or the travel distance for a vehicle v to pick up a request p. Okay, so the path assignment, which is really what this research is about. This here is shown the bi-criterion, or it's formulated as multi-criteria shortest path problem. So we have two different objectives, two criteria, two objectives. The first is the conventional shortest path objective. Again, we have another cost matrix, Cij. This is the cost of traveling on each one of the links. A link is defined by its upstream node I and its downstream node j. So that's the link, ij. You want to move through the links in the network that get you from UC Irvine's Antietam Recreation Center to the Staples Center. So which of these links, xij, do you want to move along that minimizes the travel time? So that's your first objective, equation 5. But then we have our second objective, which is not minimizing travel time, but maximizing another reward term. This is the reward for going over links that are likely to have demand associated with them. So it's a stochastic environment. You don't really know if a demand will arise along that link or at that link before you get there, but you have some probabilistic information about the expected number of travelers that are going to be there over the next hour or so. So the constraints here are the flow balance constraints. It basically just says that if a vehicle goes into a node, it must also come out of the node in the network. And then the first and the third means that it has to end at your start node O and has to finish at your destination node D. So we're going to combine these two objectives by applying a weight term to the reward. So there's a bunch of different ways you can assign a value to a weight for the reward. So one thing we learned through the process, and I kind of had an intuition going into the research project, is that you can't assign too much reward to a link. If your reward here, or really your reward times your weight, is larger than your cost, then it's just going to tell your vehicle to effectively keep going back and forth on the link until it becomes full. Which you could argue if you're outside Staples Center or Madison Square Garden after an NBA game lets out, it actually makes sense to just hang out on that link until you can fill up your vehicle and you go to your destination. But we don't want to really put that in our algorithm because that can make the passengers in the vehicle quite mad if they're waiting for other requests to get inside the vehicle by moving back and forth on it. So we got to be very careful about how much we weight the reward. So you can make it as a function of the current occupancy of the vehicle, right? If you have more people that are in the vehicle right now, you're less likely to detour away from your shortest path. And then the time slack is, okay, you have people that you are in the vehicle already. You might have made a promise to them that you'll get them to the airport by 8:45 a.m. If right now the travel time is going to get you to the airport at 8:40 p.m., you only have 5 minutes to spare, you're less likely to want to detour your vehicle outside away from the shortest path. We already covered the reward term, which is related to the potential link demand on each one of the links. So we're going to test as kind of a proxy way of testing different W values for conditions under which we're going to call the bicriterion path. So the first is when there's just one passenger inside of the vehicle and that the vehicle has no other request to pick up. So that's case one, it's the simplest case. So we're only going to look for bicriterion path in the most generous situations for the vehicle. Case two is where the vehicle has no pickup task, it only has two drop-off tasks. So it has two passengers in the vehicle, needs to drop both of them off, we're going to assign it to the bicriterion path. And then the third is the most generous, in which you have two drop-off tasks and no pickup tasks, same as two, or in which the vehicle is empty but en route to pick up a traveler. So those are the three different conditions we'll cover in the results here. So I'm going to spend a little bit of time talking about how to calculate the reward, the input parameter Rij, on each one of the links in the network. And that is, of course, going to have to be a function of where the vehicle is right now and where the vehicle is going. So the first step is constructing an ellipse. Really, we're going to call it the detour ellipse, where the focal points of that ellipse are going to be the vehicle's current location, denoted by node 316, and the vehicle's destination, or really its next pickup or drop-off that it needs to go to. Those are going to be the two focal points. The length of the major axis is going to be the distance between the current location and destination, plus some max detour. Maybe it's an absolute detour of 5 miles, or it's a percentage detour of the length between these two locations. So you have your ellipse. You can see which set of nodes are inside the ellipse and which set of nodes are outside of the ellipse. So we're going to first follow a step-by-step process here. We're going to find destination nodes within the region. So every single one of the nodes that are in the region, we're going to store the origin destination demand for each and every one of those nodes in our region right there. Okay, so I guess, yeah. So we're going to be looking at just what's shown right now. Every combination of nodes in our green region, we're going to store the demand associated with that OD flow. Now we're also going to look for nodes outside of our region, where the shortest path from our origin to the destination passes through this current vehicle destination, node 406. And again, we're going to store this origin to destination demand flows. Now we've stored two different sets of demand. You kind of already have this information because you already know that each one of these are going to be going through your destination. You're going to assign that demand from each one of those OD flows to the first link that comes out of the origin towards the destination. And that's how you're going to obtain your reward Rij on each one of these links. Now, this is just one way to do it. There are a bunch of different ways to get an estimate of the reward on each one of the links. My students think that this is a very important thing to get right. I'm a little bit more skeptical about the importance of getting this Rij term exactly right on each one of the links. I think we need to do a reasonably good job of estimating the potential demand on each one of these links. And the key thing is that the demand has to be moving generally towards where the vehicle is moving. So we don't want demand that's moving in the opposite direction, even if the origin node of that new demand is going to be on our route. Okay, so the case study. As I mentioned a couple times, we're going to use the Anaheim network. This is free and publicly available on someone's GitHub page. Sorry, I can't remember his name right now, but you can probably just Google Anaheim network, Chicago networks there, the Sioux Falls network. There's about 15 different networks that are available online. It has 401 nodes, 854 links, so it's what I'd call a moderate-sized network. We allow demand to originate or terminate at 223 of these nodes. We're going to test different case studies or different fleet sizes in our case studies. I actually thought we had a little bit bigger fleet sizes, but we'll be going from 20 vehicles to 200 vehicles. The number of requests will also vary between 100 requests in total over 3 hours and 2,100 requests over 3 hours. We're also going to vary the reward coefficient, WR, in our pathfinding approach. And fourth, we're going to test the different bicriterion conditions that I went over before. So I think in total there's 610 different experiments that we're going to run, and you'll see the results of those in graphical form. So the outputs, or what we're interested in, is the difference in performance between the bicriterion approach and the shortest path approach. We're going to use several different metrics. One is customer wait time, the second is in-vehicle travel time, and then we'll also have a combination of customer waiting time and in-vehicle travel time, which you might call total time. We also have metrics on the percentage of requests that are served, but in all of the cases that I'll be covering today, that is either 99.5% or 100%, somewhere in that range. So first set of results here, a lot to take in. I'm going to first cover up what I call the bad results. So the algorithm performs okay. We don't have amazing results yet, which is somewhat disappointing, but that's the research process. That's how it goes. You see there's a lot of variance in the performance of the bicriterion pathfinding and the shortest path. A little bit hard to explain why there's so much variance, and really trying to explain exactly where that variance is coming from is hard. But one thing to focus on is that between vehicle fleet sizes of 300 and 1,000, where the demand here is going to be, request is between 300 and 1,000 and fleet size is 100. We're calling that the slight undersupply to slight oversupply scenarios. In all these cases, generously speaking, the bicriterion approach does outperform the shortest path approach. In cases where you're heavily undersupplied, that is, vehicles are much lower than the request, or heavily oversupplied, when you have plenty of vehicles, it doesn't really matter what path you put them on. The shortest path tends to do better than the bicriterion path. So the three, let's see here. Top left is difference in wait time. Top right is in-vehicle travel time, total time, and here you can see that for all the cases we looked at, 100% of the demand is getting served. Okay, so the second analysis we're going to perform is on the reward coefficient, WR. That's how much weight is going to be applied to the reward term compared to the travel time term. Again, we have high variance in results, particularly as that reward term, WR, gets weighted more heavily. So we're going to spend some future work figuring out how much we should weight the reward term. And rather than doing what I would call a somewhat simplistic analysis we did here, which is just vary the weight under any conditions, we want to make the weight a function of the system state. So a function of the vehicle occupancy, a function of the relative supply and demand balance in the network at the current time, even looking at different regions of the network and determining if they're balanced or imbalanced. So we see, you can maybe tell here, the green line does tend to perform better than all the other ones, which is a weight of 0.1 on the weight or on the reward term, which I guess shown most clearly here. The green line is always doing better than what is effectively the zero weight line, which is red, which is such a small weight on the reward term. So giving large weights to the reward term does not seem to be a very smart strategy in most cases. Okay, and then looking at the three different conditions here, condition 1 tends to outperform conditions 2 and 3, which just means we need to be careful about when we're applying the bicriterion approach. So if the vehicle is pretty much full, or it has a set of, or several sets of pickups and drop-off tasks remaining, you're better off sticking with the shortest path approach. You only want to apply the bicriterion approach, again, in the case in which you're not conditioning on the state of the system, when the vehicle is relatively empty. It only has one drop-off, maybe only has one pickup in those cases. Okay, so some conclusions here. On average, you're saving about 3 to 5% with the bicriterion approach in the range of values where we're considering mildly undersupplied to mildly oversupplied. Not what I would have liked. I was hoping for a bigger impact, but that's how it goes. Like I said, we'll be doing some future research to improve that more. Again, it works best when you're relatively balanced between the supply and demand. We also found that the link reward weights do have an impact on the performance. So we're really gonna try to do something called hyperparameter optimization. That weight term being the hyperparameter, and the optimization meaning just running a bunch of different simulations with different reward terms under different conditions and determining what reward term should be used depending on the conditions of the system. And then the fourth and final conclusion is that this first condition does tend to outperform the second and third conditions. Okay, so this is kind of what I'm most interested in, is the future enhancements of this approach. I still think the idea is good. Again, not as good as I would have liked on first pass, but we're gonna keep kind of digging a little bit deeper. My students are interested in this as well. So the first is just simply improving the link reward estimation method to better estimate this potential demand. I mentioned this earlier, my students are really interested in doing that. I'm gonna support them on that. The second is improving the pickup drop-off resequencing when the vehicle is on the bi-criterion path. So I didn't get into this, but the routing or sequencing of pickups and drop-offs in the algorithm is based on the assumption that those distances or travel times between the pickup and drop-off locations are based on the shortest path. There's a little bit of inconsistency between them. Addressing that inconsistency is quite tough because the bi-criterion approach depends on how many people are in the vehicle at a time. But if you haven't sequenced the pickups and drop-offs yet, you don't know how many passengers are going to be in the vehicle yet. So we're going to try to close that loop, but it's a bit of a challenge. The third is to more explicitly incorporate the remaining time associated with each one of these requests into the algorithm. Now these last three are what I'm most interested in. So the key idea in the initial research is to look at where the demand is. We want to route the vehicles through the high demand regions on the links with high demand, which is a good idea, but we realized about halfway through, what matters is not just the demand, but the relative imbalance between supply and demand in that region. Going back to my Chicago example, if you already have a bunch of vehicles in your high demand corridor, or they're moving closely through your high demand corridor, you don't need to force other vehicles into that area. It's already being covered by the supply. So we're just gonna try to change how we denote the rewards on the links by taking into account where the vehicles are and where the vehicles are going, in addition to where the future demand is going to be. And this is a similar idea for the next bullet point here, which is, in general, trying to disperse the vehicles to cover the network holistically. So not assigning them the shortest paths, not all forcing them on the path that our bi-criterion algorithm puts them on, but really trying to cover the network as a whole as the vehicles move through it. Now, the other realization there is like, okay, that's what a bus network does, right? Bus lines try to cover the whole region, the main corridors, relatively consistently. On the corridors that have heavy demand, you put more buses, higher frequency on those corridors. On the slightly lower demand corridors, you have fewer buses. So how can we take some of the ideas from bus route network design and apply them to mobility on demand with shared ride services? And then the last thing, I've hit on this a couple times now, but we want to make this reward term, or the weight for the reward, conditional on the state of the system. So some of these states, obviously one is the supply-demand imbalance in the region or in the subregions, the relative vehicle occupancy, basically everything I've hit on already here. And there's ways to do that. I mentioned hyperparameter optimization is probably the way we're going to go with that. Okay, so thank you very much. Happy to take questions. I will acknowledge my students I should have done in the beginning. Dingtong Yang and Navjo Sharma did most of the work on this, particularly the computational side, and much of the intellectual work as well. A lot of conversations between the two of them and myself. Please feel free to reach out to me if you have any questions or want to connect in any way at my email right here. Thank you very much.